Welcome back. So today we're going to go through angled launches. So let's get in it. If I use my 52 meter per second bow to launch my arrow as far as possible, I need to use a 45-degree angle. So how far could I launch my bow if I had an initial launch speed of 52 meters per second and an angle of 45 degrees? Well, let's draw a picture. Okay, so the question is asking how far I would go. So that's delta x in the x. So in order to solve that, my variables, I'm going to need to look at this point right here. So x dimension at the end. And we know from the horizontal launch lab that the x dimension, all of the horizontal velocities are the same. And so my v is just v sub x. My delta x of x is what I'm looking for. And then my time, hint hint, is probably going to be gathered in the y dimension and then used in the x dimension. Now that is going to be the total amount of time. So we'll just go ahead and write that t-tote and we'll leave it at that. Okay. Now the y dimension, the strategy here is that I'm going to find my time and my velocity in the I'm going to find my time in the y dimension. I can find my x doing some trig. And so let's set up my y dimension. And I'm going to focus on this point right here at the top in the y dimension, and then I'll be able to double my time so I can use it in the x dimension. So I'm going to do y dimension at the top, and so my delta x in the y, v naught, a t half. My acceleration is opposite of my frame of reference, so negative 9.8. My v naught, I'm going to do some trig over here, I'll show you how to do that. And then my v at the top is going to be 0. And my height, I don't really know. I could find it if I needed to. Okay, so the strategy here is I'm going to use trig to find my v naught, and then that'll solve for my time. And then I'll double that to get into my x dimension, and then I'll use some trig to find my v sub x, and then I'll solve for my delta x in the x. Okay, so I mentioned the trig a few times, so let's look at this piece. I understand that this piece has an x component and a y component. We're going to call that v naught x and v naught y respectively. Now, because of the trig properties, so right, the sine of theta is equal to opposite over hypotenuse, and the cosine coa adjacent over hypotenuse. I want to know what these are, right? And so the sine is in the opposite, this v naught y is in the opposite position of my angle, and the v naught is in the hypotenuse here. And so I'm going to put this into terms of my velocities, and so v naught y is my opposite, and my v naught is my hypotenuse, and then I can rearrange that a little bit. So it says v naught sine 45 equals v naught y. So I'll pull that over here, a little easier to see. V naught sine 45. Okay, and that, as long as your angle goes to the horizon, this is going to become very, very quick for you. Okay, we'll do the same thing over here for v naught of x. V naught of x is in the adjacent position to this angle, and so that would be the cosine 45 is v naught x over v naught, and then divide that over. And so I have v naught cosine 45 is equal to v naught x. And these are going to be really important to understand as we go forward, okay? Using the independence of dimension, I want to know how far the velocity in the x gets my object in the x, right? So we need our variables to agree with each other, and so I only want the velocity in the x to go into my x dimension calculations. And just the same thing, I only want the velocity in the y, just like so my vertical launch, I'm going to treat this as a portion of this is going straight up and then straight back down. All of those nice properties we talked about, they work if I can tease out the y dimension piece of that. With this understanding, my v sub x is going to be 52 cosine 45, and that'll be a number we can calculate. And then my v naught y is going to be 52 sine 45. 36.77 meters per second. And they're the same because the angle is 45. So exactly, you can think of it as half, right? Exactly the same portion is in the x as there is in the y. All right, so I'm going to start with the y dimension. I'm going to get to this time, so I can double it over. So I'm going to use, and then I'm going to the top point here, and so I know that this term is 0. I get 3.75 seconds, and that gets me to this point right here. So I'm going to take that time, I'll multiply that by 2 to get to t tot, 7.5 seconds. That's going to get put into my x dimension. And then from there, now I have all the variables I need. So I've got v equals delta x over t. I get 276 meters. And so if I had a launch velocity, the capability of my bow and arrow to go 52 meters per second, and I hit the 45-degree angle, that's kind of like the magical mark. That's how I get objects to go as far as possible. If I go steeper, they go higher, but they land shorter. And if I go shallower, they run into the ground sooner because they have less air time, less height altogether. So there you go. This is a typical angled launch looking to solve for distance, keeping in mind that we started in the y dimension. We made sure that all of our variables agreed with each other. I was very careful to make sure my t half in the y dimension got translated into my t tot in the x dimension, and then I chose a new equation and I went on from there. Okay, so this is a pretty typical angled launch scenario. We're going to do one more. We'll go ahead and solve for height. So I'll leave a lot of this stuff up here and we'll just kind of pick a few different equations. If I carry over that half time here, I'll go ahead and pick a different kinematic equation and solve for height. So delta x is equal to v naught t plus 1/2 at squared. It's really critical that the variables agree with each other, so we're just going to double check. So my delta x is going to be the displacement in the y dimension, my initial velocity in the y dimension, my t half, and the a, although we don't need to, this is the acceleration in the y dimension. Okay, so it's in the form that I want, and I can't make any terms go away. And so I'm just going to go ahead and plug in my numbers. Meters. So there you have it. Your v naught x is going to be v naught cosine theta, and your v naught y is going to be v naught sine theta. This will hold true 99% of the time unless you're doing something really, really weird. But remember, if we keep our angle to the nearest horizontal, like we did here, then these rules should apply. And then we Made sure we are looking at t half versus t total. That's important to keep track of. My v sub x is the same all the way through, no matter where I am in the trajectory. The x dimension velocity does not change. There is no acceleration. It's a constant velocity. And then the other thing we looked at was the acceleration here was negative because the force due to gravity, which causes this acceleration, is down all the time, and it's opposite of my reference point. So that's what makes that negative. All right, that's all I got. Thank you.